There, good to go. Have a good session.
Okay, thanks, Kay, and thanks, Kevin. Hi, everyone. Welcome to the session of Zero Knowledge Proof of Asia Crypt 2020. I'm Chang. Going to co-chair the session with Jay Hong. So there will be 6 talks in this session, and for a bit of logistics for the speakers, and each of the talk will be 5 minutes, and then we're going to be follow up with a couple of questions. And if we still have questions left, then we can have more Q&A at the end. So the first talk will be cryptography from one-way communication on completeness of finite channels by Shweta Agrava, Yuval Ishai, Yael Kushlewicz, Varun Narayana, Manoj Prabhakaran. We know the Prabhakaran and Alon Rosen. So Varun will be giving the talk. Varun, if you are online, can you share your screen?
Yeah, hi. Thank you. Am I visible?
Yeah.
And
Yeah, it works well.
Okay, so I'll go ahead and start my presentation. Hi, everyone. Thanks for joining this presentation. My name is Varun Narayanan. This is a joint work with Shweta Agrawal, Yuval Ishai, Eyal Kushlewicz, Manoj Prabhakaran, Vinod Prabhakaran, and Alon Rosen. In this talk, we will look at the secure computation capabilities of a noisy channel when there's only one directional communication. So let me go ahead and describe what a channel is to start off with. So a channel is a mathematical model of a noisy, memoryless communication link. It has a finite set of inputs and a finite set of outputs, and it is completely described by the distribution over the output symbols caused by every input symbol. So one run of the channel will look like the sender setting an input X to the channel and the channel choosing an output Y with probability P of Y given X. The model of one-way secure computation was introduced by Garg et al. In 2015. The objective is to realize a sender-receiver functionality securely with only one directional communication over the given noisy channel. So by a sender-receiver functionality, I mean a possibly randomized functionality in which the sender has only an input but no output, and the receiver has only an output but no input. And because of the one-directional communication one directionality of the communication, the one-way secure computation protocols, or OWSE protocols for short, has a simple structure. So the sender with an input, say A, is going to encode the input using an encoder S and sends it over to the receiver, making possibly multiple uses of the channel. And the receiver, on receiving the output from the channel, will try to compute his output using a decoder R, applying it to the output of the channel, so R of Y. The correctness of the scheme would require that the receiver's output, R of Y, is distributed closely to the output of the functionality, F of A. We will also require security against the sender and the receiver. So the security against the receiver says that the receiver's view, which is the output of the channel in this case, does not reveal anything more than the output of the functionality itself to the receiver. So this means that the sender cannot simply encode his input, her input, uh, using an error correcting scheme and send it over to the receiver, because this will breach the privacy against the receiver. So the privacy against the sender would require that the sender only learns that the output of the receiver is distributed according to F of A for when the sender has the input A. So for any encoding that the sender sends through, the sender learns nothing more than this. So specifically, the sender cannot simply compute the output herself and send it over to the receiver in using an error correcting code. So this model has many applications. Many of the cryptographic tasks can be modeled as sender-receiver functionalities. The OWSE gets its interesting applications because of this. So one remarkable use is coming up with truly interactive, non-interactive zero-knowledge proof without using any trusted common randomness setup. We will also have a this kind of zero-knowledge proofs will also have some desirable properties like deniability and non-transferability, etc. Another application is randomly generating puzzles without giving any party an advantage in solving them. OWC can also be used in realizing randomized signatures, which have applications in eCache, non-interactive certified PKI generation, etc. Our work is extending many of the results from the Gargeta's paper from 2015. In their paper, they showed that binary erasure channel and binary symmetric channel, they are not complete in the OWC model with negligible error. We say that a channel is complete in the OWC model if it can compute every functionality securely in the OWC model. And by negligible error, we mean that the error is negligible in the number of uses of the channel made by the protocol. In our work, we extend this result and we show that no finite channel can be complete in the OWC model with negligible error. In the positive side of things, the previous work had shown that the class of all string ROT channels is complete in the OWC model with negligible error. Here, string ROT channel is the sender-receiver version of the string oblivious transfer functionality. So the sender has a pair of string inputs, and the receiver will receive one of these strings uniformly at random. In our work, we show that if we are ready to relax the negligible error guarantee to an inverse polynomial error guarantee, then there indeed is a finite channel, which is the bit ROT channel, that is complete in the OWC model. Further, the previous result also showed that for specific channels like BEC and BSC, zero knowledge functionality can be realized in the OWC model. In this work, we completely characterize the class of all channels that can realize zero knowledge in the one-way secure computation model. So let me briefly describe two of the positive results that we have. The first one is about realizing.
Sorry, Varun. Probably you should wrap up soon. So every talk is only 5 minutes.
Oh, okay. So how much time do I have left?
-1.
Oh, okay. So in that case, I'd like to say that our construction of string ROT using bit ROT uses an average case RAM secret sharing scheme, which might be of independent interest. And the construction of the zero knowledge protocol using a non-trivial channel uses a geometric interpretation of the channel to design the protocol and analyze it. So please take a look at these two things, go through the main presentation, and thank you. Have a good day.
Thanks, Varun. Is there any question from the audience? I have a quick question. So it seems like at least second part of your major result is about impossibility, right? Essentially, you show the channel is the string OT cannot be built from the noisy channel, right? With negligible error.
Yes.
So do you see any like way to strengthen the assumption a little bit to circumvent the impossibility? Like what a minimum trust component you can add, for example?
It's already known that if we allow interaction, then every non-trivial channel can be used is complete in the interactive model. So the non-interactivity is exactly the caveat here. That's exactly what is causing trouble. And when we have non-interactivity, like our positive result says, if we are ready to relax the security guarantee, going down to only inverse polynomial error, we can realize it with many channels. And one of the open problems is characterizing what channels can realize, be complete in this when we are asking only for inverse polynomial error.
I see. Thanks. Any other question? If not, maybe Jae-Hong, you can start the second one.
Okay, thank you. And I'm Jae-Hong, another co-chair of this session. And actually, the second talk is about succinct functional commitment for a large class of arithmetic circuits. The authors are Hegel Limma and Catalina Pavlik. Yeah, actually, Catalina was supposed to give a talk today. However, unfortunately, she cannot attend the current session. So yeah, actually, she provided a 5-minute video, and so we will play her video now. If you have any question, I think you can freely contact her via her email given in the paper. So Kevin, or Kay, could you play her video now?
Hi, I am Katarina Pavlik. This is a teamwork with Helga Litma. We are from Simula UAB, Norway. The title of my talk is Succinct Functional Commitment for a Large Class of Arithmetic Circuits. In recent years, several generalizations of commitment schemes were introduced. The vector commitment allows committing to a vector of messages and later opening the commitment at any position of vector. In a polynomial commitment scheme, the committer commits to a polynomial and after getting an evaluation point, opens the commitment to the evaluation of the polynomial in that point. The latest generalization by Liebert et al. Formalizes the notion of functional commitment, which allows committing to a vector of messages, which can later be opened to a specific function evaluation. The functionality is covered by Liebert restricts to linear maps. Succinct polynomial commitment schemes have recently become very popular since they can be used to construct updatable snarks. Since in several applications, for example, in cryptocurrencies, one has to run many instances of succinct functional commitments in parallel, there is a recent surge of interest in aggregatable succinct functional commitment schemes. But there is a large gap between functional classes for which a succinct functional commitment scheme is known and the class of all efficiently verifiable functions. So we put a goal to fill the gap. We construct a succinct functional commitment scheme for a large class of circuits under a falsifiable assumption, and succinct and falsifiable are here keywords. In a functional commitment scheme for a circuit, committer commits to a secret input vector alpha, obtaining a functional commitment value. The goal is to allow the committer to later open it to the value of the circuit xi, where beta is a public input that is chosen by verifier before the opening. Our functional commitment scheme satisfies the strongest hiding, namely, it is zero knowledge hiding that guarantees hiding in the sense of simultaneity. Our scheme satisfies the relation binding, what allows the committer to open to two different vectors as long as the value of function is the same. And our functional commitment scheme is succinct, that is both the commitments and openings have length that is constant in size of both secret and public vectors. Here is a high-level overview of our technical contributions. The construction of the new functional commitment scheme consists of the following steps. At the beginning, the original circuit is compiled. The circuit computing the fixed function is compiled to a circuit consisting of 4 public subcircuits, and we need this division to prove evaluation binding under falsifiable assumption. Then representation of the compiled circuit in the QAP language, which snarks usually use, and the last step, construction of succinct functional commitment scheme for the QAP representation by using snark techniques in a non-black box way. Our scheme is inspired by snarks, namely by the growth-efficient snark for arithmetic circuit satisfiability, more precisely, its improved version by Litma. A non-succinct functional commitment can be constructed from a non-succinct NISC using NISC as a black box. However, while non-falsifiable assumptions are required to construct snarks, we want to construct succinct functional scheme or commitment scheme under weaker assumptions. Succinctness makes our task harder. Some conceptual differences between snarks and functional commitment objectives are gathered in the next table. They have different security properties to achieve. In the case of snarks, prover has full access to input. In case of functional commitment, it gradually gets it and later constructs the argument based on full info. For snarks, argument consists of a singlet string. For functional commitments, we have division due to careful separation of public and private inputs. The compilation of original circuit we use reduces the circuit class we can handle. Here to the right, we see this compilation. The red circuit here applies to private input only, the green circuit to public input, and they are unrestricted. And the next circuit, circuit high, he combines outputs of previous two circuits and has a restriction. For security reasons, this subcircuit is restricted to have multiplicative depth 1. We cannot handle all circuits due to the restriction of evaluation binding to a falsifiable assumption. Thus, our new succinct functional commitment scheme will work for all circuits that have a polynomial size compiled circuit such that that concrete subcircuit phi has multiplicative depth 1. We study the class of compilable according to the given definition arithmetic circuits. It appears the resulting class is wider than the class of sparse polynomials, but smaller than the class of polydegree polynomials that have polysize circuits. We prove the evaluation binding of our scheme under the new computational span-over assumption in source group. The proof differs significantly from the knowledge soundness proof of snarks. The new span-over assumption states that it's difficult to output the next sum together with the coefficient vector delta, where fi are not in the span of set R. It is reminiscent of the well-known computational over assumption in a source group. We provide a thorough analysis of the new assumption. First of all, we show that it follows from the more conventional over assumption in target group. Then we prove that it holds under a hash algebraic knowledge assumption. And also we use a dash Q approach to prove that in composite order bilinear groups, the computational span over assumption in target group holds under appropriate subgroup hiding assumption. Thanks you for listening. The full version of the talk will be available on YouTube.
Okay, thank you. And actually, if you have any questions, previously I told you that you can directly contact her, but if you have any question, please leave your questions on the chat IESL.org. Okay, then maybe, yeah, Katalina can answer later, can available. Okay, Kian, could you?
Okay.
Yeah.
Okay. So next talk is crowd verifiable zero knowledge and end-to-end verifiable multi-party computation by Fotini Baltimsi, Aglas Gias, Tomas Zakaziras, and Bingshen Zhang. Bingshen, you can start. Bingshen, we cannot hear you.
Okay, I unmuted. Can you hear me?
Yeah.
Okay, good. Okay, hello everyone, I'm Bingshen. Today I will talk about cloud verifiable zero knowledge and end-to-end verifiable MPC. So first, what is the end-to-end verifiable MPC? So let's look at the conventional MPC. In a conventional MPC, we have parties and they want to jointly compute some function, let's say f x1, x2, x3, and we have a certain goals. For example, input privacy, P1's input is unknown, or the output correctness, or input independency, or fairness, or guaranteed output delivery, etc. All those security usually may be captured by a UC ideal functionality. But I want to point out is that in traditional simulation-based MPC protocols, we usually assume some of the players are corrupted, which means not all. If all of them are corrupted in the simulation, the simulator does nothing because simulator only simulated the honest parties, then which means the simulation is trivial. And we just do not consider this case. However, currently more and more MPC protocols are used in the client server mode, which means the MPC players are not the input nodes. We have some clients, and those clients are output nodes. And we have some MPC players, those are called servers, computing nodes. The computing nodes do not have the data from the clients. Now here's the question, if all the computing nodes are malicious, what's the security guarantee? If you think about it, usually we don't have privacy because it's MPC protocol. If all the parties are malicious, then we have no privacy for sure. But how about the correctness? This is known as verifiability or auditability. So in a publicly verifiable MPC, we need to slightly modify the architecture. We need to put an additional node called the bulletin board, trusted bulletin board, which can be realized by, for example, broadcast channel or Bitcoin, etc. The idea is as follows. The MPC players will also put some transcript or some proof on the bulletin board during the computation, such that everyone look at the bulletin board can verify the computation is correct. So that if I'm not a part of the MPC player, I give, for instance, privacy preserving machine learning, I give my data to them and they will train a model for me. I can ensure the model is correct. This kind of work has been studied previously. For example, BDO14. BDO14 is published at SCN14. They actually modified the speed protocol, attach a commitment to each shared value. And the key point is the secret sharing is homomorphic, linearly homomorphic. The commitment is linearly homomorphic. They have exactly the same message space. So they share exactly the same homomorphism. And the player can put the commitments on the bulletin board. The idea is as follows. The MPC player usually use a homomorphic operation on the shares. If they do so, the auditor, anybody, can look at the commitments on the bulletin board, can do exactly the same operation because they share the same homomorphism. When the MPC player open a share, and they will also open the corresponding commitment on the bulletin board. So everybody can perform exactly the same computation on the commitments on the bulletin board. Therefore, they can verify the result. The security guarantee is of BDO is if at least one of the server is honest, then privacy and correctness both can be achieved. If all the servers are corrupted, then only correctness. And the assumption is for example, they need a commitment key. They use Patterson commitment. For simulation soundness, the commitment key need to be done in the CIS model. Because it's not structured, you can also use RO to provide this. In the paper, they use a random oracle for the NISC protocol, NISC proofs. And similar problem also have been studied, for example, universally verifiable MPC. They use SV15. They use threshold homomorphic crypto systems. They also in the random oracle model. In this work, we propose a new concept called end-to-end verifiable MPC. Basically, we extend the existing model. We consider the Byzantine client behavior. We separate the client from the user. For example, if I'm a user, then when we separate it, the C1 is my computer, I'm U1. So if we do that, we actually have more refined security consideration. For instance, what if I am honest, I'm a human, my computer is malicious, my computer get hacked, which means C1 is malicious, U1 is honest. But in the conventional model, we never be able to consider this version. Secondly, we want to have this kind of protocol in the standard model or in the plain model, which means no RO, no setup, no CIS, except the BB. In our model, the server and the client are stateful, probabilistic, interactive two-way machines. The humans have limited computational power and entropy. Basically, we want to capture the fact that humans are bad randomness generator. Usually, they cannot generate a random string with sufficiently entropy that is exponentially hard to guess. And secondly, we think human cannot manually perform cryptographic operations. So we make
probably you also
time is done.
Yeah, you should
okay.
wrap up very soon.
I will wrap up. Okay. So in order to do so, we propose a new function, a new primitive called cloud verifiable zero knowledge. It's like the normal Sigma protocol, but we have multiple people cloud. It's very hard to do. Why? Because some of the verifiers are malicious. It's known as non-oblivious bit fixing source. You cannot do it by one round coin flipping. In the Sigma protocol, basically everybody give you some coins and you want to jointly produce something. We propose something called a coalescence function. Due to the time limitation, I will skip it. And for that, we actually constructed the VMPC. Because the time is too short, I will directly conclude. We prove our VMPC protocol in the HEUC model, which is very close to Andrew model. We use adaptive one-way function, input delay ZK, and commitments. Thank you.
Thanks, Bingshen. Nice talk. Is there any question from the audience? It seems no from the chat.
I do have one. Hello, can you hear me?
Yes.
Yeah. So yeah, the question is, you mentioned that the bulletin board could be realized by basically a broadcast channel. So which parties will be doing this? I guess the Cs, right? Like when you don't separate C and U, so you just have Cs. If the bulletin by whom would it be realized?
Okay. In this work, we did not realize this. In reality, if you consider, for example, end-to-end verifiable e-voting, which has been realized long before the popularity of the bulletin board. The blockchain. So what they do, they realize the bulletin board by a replicate state machine, or they use 3 servers to make sure there's no single point of failure. The requirement for the BB is everybody will read the same data. The most important thing is that the BB will not present the same view or different view to different people. Let's say the BB first see my IP. If I'm from China, it will present one version to me. And if it's from US, it present another version, then there's a problem. In this work, in the paper, we did not discuss any realization of the BB. It's just an ideal functionality. In reality, if you want to deploy this VMPC protocol, and you can use a blockchain.
Okay, yeah. My remark was just that you would need then to have some assumption on the number of parties that can be corrupt to realize this BB in practice. So I was just wondering which parties will be doing so, because you want all your keys to potentially be corrupt. So I would assume you have like a different set of parties where you would have to limit the corruption to be able to realize the bulletin board. But that was just what I was wondering.
Oh, yeah. This is because in our model, we actually consider very extreme case. We consider all the servers are malicious, all the clients could also be malicious. So in that case, nobody is realizing the BB. If at least one server is honest, then yeah, we can have broadcast channel to do this.
Okay, thank you.
Okay, very nice conversation. So probably due to the time limit, we don't have time for a question now. We should move directly to next talk.
Okay, next talk. The title of next talk is a non-interactive composition of Sigma protocols via Sheldon hash. The authors are Masayuki Abe, Miguel Ambrona, and Andrei Bogdanov, Miyako Okubo, and Alan Rosen. Masaki Abe will present.
Okay, thanks a lot. Do you hear me?
Yes.
Okay, so this is a joint work with Miguel Ambrona, Andrei Bogdanov, Miyako Okubo, and Alan Rosen. I'm Masayuki Abe. So our starting point is a Sigma protocol, which is a special kind of proof system where approver and verifier exchanges 3 messages to see if statement X satisfies a relation R. For disjunctive composition, we can use well-known technique by Kramer, Dangard, and Schumacher. Here, the prover, knowing a witness only for statement X1, executes a simulation on statement X2 with a random challenge chosen by herself. Then, the prover will secretly share the main challenge with this random string as a challenge, as a share. The other side of the proof is done by using this share as a challenge. Namely, the prover has full control over one of the challenges. This is perfectly fine in the original CDS composition, but it causes some limitations that we try to overcome in this work. We propose a very simple modification over the CDS composition, which can be summarized in one sentence. Hash each share before using it as a challenge. Now, in our modification, the challenges are generated by a hash function applied to shares assigned to the statements. So, why do we like to do this? There are 3 benefits. The first is an efficiency improvement by recycling transcripts for repeated statements. Consider a compound statement where the same statement appears multiple times in different clauses. In such a case, the original CDS requires multiple runs of the underlying Sigma protocol on the repeated statement. With our share then hash, all shares assigned to the same statement are hashed together to yield a single challenge. Accordingly, we only need to run a Sigma protocol once for a statement, no matter how many times it appears in the compound statement. The second benefit is that it allows to compose more general protocols. The original CDS composes protocols having 2 special soundness. But with our modification, you can compose k special sound ones for k equal or greater than 2 that includes sound-like protocols used in lattice-based cryptography. The final point is that our modification allows to prove unforgeability in non-programmable random oracle model as a signature scheme. This avoids impossibility result from the previous work by Fischlin, Hassar, and Jensen, where they observed that it is hard to see which instance in a compound statement is attacked due to the parallel structure of the CDS composition. The additional hash queries in our modification helps to identify attacked instances. For this, we only need to observe the order of the queries and do not need to program their output. Thus, we have a proof in a non-programmable random oracle model. Now, in summary, we have proposed a simple and generic modification over the CDS plus Piaget-Shamir composition of Sigma protocols. And we observed that such a tiny change brings several nice advantages. Thanks for listening.
Okay, thank you. Is there any question? Okay, I have some question. Actually, in your slide, there are 3 advantages of your modifications. I think first one is about efficiency, and last 2 about security. And in your people, you mentioned about some applications such as anonymous credentials and link signatures. So if we use your modified method instead of CDS transformation, so what is the performance improvement for such applications?
Okay, the only additional workload are those hash computations. So I believe that as long as the original CDS works well, I think this overhead should not be a very bad overhead when we plug in our protocol, our scheme to the applications. So I would say this modification should work almost in any applications that the original CDS works.
Okay. Yeah.
Is it good? Yeah, and even in some cases, it will even make it better because when, as I said, as a first benefit, when some statements are repeatedly appearing, then the total proof size will be shorter than before.
Okay, yeah. Thank you. And
yeah, actually, I have a question.
Yes.
I have a immediate follow-up question, actually. First, very nice work.
Thank you.
So when you mentioned the proof size can be shorter, I can totally understand essentially the new proof size will be depending on the number of variables, right? But once you do the transformation to make it like a 3 CNF or 3 DNF, then essentially it seems like the size will be determined by the number of clauses, right? In this case,
right.
Seems challenging to get. So it's more like you can make the constant factor much smaller, but it's hard to get asymptotic improvement, right? Is that the case?
I think it's the actual saving will depend on the number of clauses, of course. So it's kind of tough to estimate what the asymptotic improvement. I don't know. It really depends on the type of statement you have.
Sure.
But as the number of repetition increases, then you get more savings, of course.
Sure. But does this saving can also happen when you just reformulate it to get it to a 3 CNF? It looks like it's challenging to make a number of variables smaller than the number of clauses, right?
Right. Yes. You're right.
Nice. Okay.
Thanks.
Great.
Okay, thank you for a good conversation. And I think there is no more question from the group. Okay, so let's move on to the next talk.
Okay. So next talk will be succinct Diophantine satisfiability arguments by Patrick Toa and Damien Vanot. And Patrick will give a talk. So Patrick, the stage is yours. You are muted. Patrick, can you unmute yourself?
Yeah, sorry. Yeah, I just couldn't find.
Okay. Yeah.
You hear me now, and you can see my screen.
Yeah.
Okay, perfect. Okay, so So yeah, this work is on succinct Diophantine satisfiability arguments. It's based on German work with my former advisor, Damien Vernier. So just as a brief reminder, a Diophantine equation is just a multivariate polynomial equation with coefficients in Z, and for which a solution are also solved in the integers. So it can be represented by basically such an expression. And in 1970, the celebrated theorem of Matisevich basically gave a negative answer to Hilbert's strength problem, which consisted in determining whether it was possible to always decide if a Diophantine equation had a solution or not. So since 1970, we know that the answer is no. But it might actually be possible for a prover to be able to prove to somebody who knows the solution to a Diophantine equation to prove that he or she has a solution to the problem and do so in zero knowledge. And this is the problem that we try to consider in this paper. But first, why would one first be interested in such equations? And actually, the reason is that already from a complexity theory point of view, actually several NP-complete problems can be encoded as Diophantine equations. So like, for instance, we just saw some Boolean formulas. So basically any the circuit satisfiability problem can be encoded as a Diophantine equation and easily. It's the same also for 3-sat, obviously. Even the graph coloring problem can be encoded as such a polynomial equation. The Hamiltonian cyclone problem as well, and even the integer linear programming problem. Those problems can readily be encoded as Diophantine equations. So that's why we're interested in it. And possibly more specific to cryptography, the problems of proving knowledge of signatures. So for instance, I just quoted in this case, the case of RSA or ECDSA signatures can also be encoded as Diophantine equations. Also the problem of verifiable shuffling, which basically consists in proving that two lists of committed values are just permutation of one another. This problem, for instance, has applications to mixed nets and to voting schemes. And this problem can also be easily encoded as a Diophantine equation. So this is actually why we're interested in them. And so it means that if one could prove knowledge of a solution or such a statement via Diophantine equations, then one could solve many cryptographic problems. But on the other hand, arguments for all NP in over fields of final or prime order already exist. And the first one was due to Gross, Ostrowski, and Sahai. So one may wonder, why would one need a Diophantine satisfiability argument in addition to that? The first answer to this question is that for certain problems, the upper bound might not a priori be known on the solution. So for instance, for the integer linear programming problem, there might be no a priori upper bound on the solution, which means that if the parameters are generated before the problem instance is even known, then the argument could be unusable simply because there will be an overflow and then there might be a reduction modulo prime. So that's one problem. The other observation is that if one were to use, for instance, arguments for all NP in over fields of prime order, one will first have to compile the problem that one is interested in into a circuit satisfiability problem. And actually, the one from Ostrowski and Sahai is actually for Boolean circuits. So one would first have to compile the problem. And doing so may at first not be easy, at least not as easy as writing down a polynomial equation. And also this compilation may actually incur like a blow up in the size of the circuit and in the size of the problem, and then result like in a computational overhead and also in bigger proofs. So be able to directly argue for the satisfiability of these equations may basically circumvent this extra issue and actually lead to much shorter proofs. And this is what we were actually interested in. So in this paper, the first thing we had to build to be able to build this Diophantine satisfiability arguments were integer commitment schemes. So Damgard and Fujizaki already gave one in 2001. But the issue there is that these integer commitment schemes are over hidden order groups. And these hidden order groups might not be cyclic. So one issue there is to be able to prove that the bases are in your commitment, which basically look like Peterson commitments. One has to prove that these bases are in the subgroup generated by an element. And these proofs have to be included in parameters. And the problem is that if there are several bases, say n, then the size of the arguments of Damgard and Fujizaki schemes where of this order, where lambda is the security parameter and is number of bases, and BEG is an upper bound on the bit length of the hidden order group elements. So we first proposed a new integer commitment scheme that like significantly shorter proofs in the parameters. So that was the first step. Then we proposed an inner product argument over the integers, and using that, we could actually also using a new algorithm that we proposed to for any polynomial equation, we could get our Diophantine satisfactory arguments. And these Diophantine satisfactory arguments have a communication of this order, where delta is the total degree of the polynomial, L is the size, is the maximum bit length of the witness, and nu is the number of variables. And H here is the height of the polynomial, so the bit length of the highest coefficient in the polynomial. But actually, Damgard and Fusaki in your 2001 paper actually could give a multiplicative argument. So if you have three commitments, C1, C2, C3, they could prove that the underlying openings X1, X2, X3 satisfy X1, X2 times X2 is equal to X3. So actually using the multiplicative arguments, one could already argue satisfiability of Diophantine equations. But we actually show in our paper that an estimation that the lower bound on the complexity of the arguments will be of this order. So comparing the two orders, one can see that in most cases, we actually, because of the binomial coefficient, we actually have like an exponential decrease in the size of the parameters. And we also applied our Diophantine satisfactory arguments to the aforementioned problems, and gave basically an estimate of the size of the proofs in the end. And in the full paper, of course, or in the full presentation, I explain how these arguments are constructed. And there are also open problems, which essentially the ones I listed there, but they are not restrictive, is how to reduce the verification time, and perhaps also how to be able to aggregate such proofs. Because if one wanted, for instance, to prove knowledge of several signatures at once, then if one could aggregate such proofs, then one could get much shorter proofs, and this could have applications to, I don't know, I would guess also blockchain technologies and the like. So that's it for this presentation. Thank you very much, and please, if you have any question, get in touch.
Yeah, thanks, Patrick. Nice talk. Is there any question from the audience? We can take one quick question, probably. Seems not from the audience. I have a quick one. So you mentioned earlier in your slides, you said that this Diophantine equation can be applied to ECDSA, right? Would your technique bring any efficiency improvement when you want to prove certain property about ECDSA signature compared to the existing general techniques? Like
to prove properties about the ECDSA signatures, or proving?
For example, like I commit a signature which is ECDSA signature, something like that.
Mm-hmm. And which property do you want to prove that you know on, or what else would you want to prove?
I'm just saying because in general, ECDSA is a bit challenging to do the efficient proof, right? Does your work give some efficiency improvement?
So I wouldn't be able to tell what was done before because I wasn't familiar with it. But in our work, there's definitely a clear estimate of how big the proof is in the end, and also how much time it takes to verify.
Okay.
I can look it for the number in between.
That's okay. So it's in the paper, right? We can look in the paper.
Yeah. Okay.
That's great. Thanks. Jae-Hong, probably we can move to next.
Oh, I'm sorry. Yeah, I'm muted. Okay, let's move on to the last talk on this session. Last talk is about the individual simulations. The authors are Yi Deng, and are you ready, Yi? Oops. You're muted.
Okay, can you hear me now?
Yes.
Okay, thank you. And this is Yi Deng, and I will talk about the individual simulations. And first, I give a brief introduction to the problem. And this is a typical crypto theorem, which says if assumption X holds, then AB, the protocol AB is simulatable. We often prove such a theorem by universal simulation, in which we construct a universal simulator and then show that for every adversary B, F can, the simulator can first or distinguish or breaks the assumption X. However, we also note that for most security definitions, we are only required to provide an existential proof or individual simulation. That is, we are only required to show that for every adversary B, there exists such a simulate. Note that in the later case, S can depend on any structure properties of the specific adversary B. It seems that the individual simulations is much more powerful, and indeed this is the case. In this paper, we show a individual simulation strategy and then construct several protocols that breaks the black box barrier on the round complexity. And the idea is the following. We start with a very simple two-round protocol AB, in which the B sends an MP instance Y to A, and A responds with a message M. We assume that this protocol enjoys two good properties. The first is that loading a witness to Y will enable us to give a successful simulation. And then the second property is distinguishing honest message M from a dummy message that is equivalent to extracting a witness to Y. The problem is, in this case, how to simulate the view of the adversary B. We firstly observe that there are two cases in which the simulator can win. The first is if the simulator succeeds to extract a witness to Y, we are done. And when the second case is that when the simulator S fails to extract the witnesses, then no other efficient algorithm can succeed. In the later case, note that by the second property of this protocol, when S fails to extract a witness to Y, then S can simply send back a dummy message to B, which is indistinguishable from the real-world interaction because of the second property of the protocol. And of course, the black box extractor would fail in this case because we have low chance to rewind in the adversary B. Then we sort to an individual extractor, which can depend on some properties of the algorithm B, specific algorithm B. First, we view that the algorithm B as a MP instance sampling algorithm, and fortunately, we are able to show that there exists a T epsilon optimal extractor for this specific algorithm MP sampling algorithm B. Here, the T can be actual polynomial, and the epsilon can be actually inverse polynomial. And then we prove that for every MP instance sampling algorithm B, there exists an optimal extractor of polynomial size such that for every second C of size T, the probability that the extractor fails to extract a witness to Y, but the second C succeeds is less than epsilon. And we can extend this lemma easily to the setting where the algorithm B outputs a multi-MP instance simultaneously. And now with such an optimal extractor E, we can construct a simulator S for this protocol. And then the S first applies the optimal extractor to, and then tries to extract a witness to Y. If the extractor succeeds, then we are done. If the extractor fails, then the simulator can just send back a dummy message to B, which is indistinguishable from the real world interaction. is guaranteed by the second property of this protocol. And our constructions now realize a key tool, which is a variant of Rabian's encryption scheme. Actually, this encryption scheme is can be viewed as a Godric level approach to encryption based on the factoring assumption. And from a result by Temple and Wall, we know that for any undistinguished ciphertext is equivalent to extracting a prime factor to the public key. And we will use these results to establish the second property of the protocol and give some constructions like this, in which the B sends a public key that is a long integer, and A sends back some ciphertexts under the public key. And then we will give very simple constructions here. I just, because I almost run out of my time, I just refer audience to my paper for construction details. And this is our contribution. And we show that on this very simple individual simulation strategy, we constructed two protocols that break along black box barriers for the first time. The first is a two-round SOA secured commitment, and the second is a three-round concurrent zoology in the BPK model. And both enjoys the TF simulatability. And using this idea, we can also simplify the constructions and the security proofs of the existing through 2 or 3 round weak zoology protocols in the plane model. Thank you.
Thank you. Thank you for nice talk. Any questions? Okay, I have a question. I think it could be a stupid question. Actually, you presented 2 applications of your techniques, individual simulation. And is there any other potential applications of your technique or other protocols that individual simulation technique may not be able to be applied? Did you try to apply your technique to the other applications?
Yes, I try to apply the same techniques, but for some we know we can try to remove the to lower the assumption, and now we are trying to base these protocols on different assumptions like LWE and something else. But I think this tactic can apply to some multi-party computations, is because this is in which we often use zero-knowledge protocols.
Okay, yeah, thank you. And any other questions? Okay, if there is no further question, then maybe I think we can finish this session. What do you think, Kyung?